All right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1103. Let's jump into it. Okay, there we go. Before we begin, I think everyone in this class actually sent me their availability but I know that the coaches were meeting yesterday and they mentioned that they mentioned that they didn't have the availability for everyone. So make sure that your team actually sent it to me, and if not, send it to me today within like an hour after class or something. Okay, so beyond that, we are going to begin probability. So very excited to do that. We've been teasing this for a long time. We started out with some probability teasers like over a week ago. Already started getting you to think about this kind of thing, but now we're going to start to make it more mathematical. We're going to start to put rules to this thing, right? So that our intuition doesn't lead us astray. So let's actually jump into it. Going to start from starting from the bottom. I'm not really going to assume most of you know much about probability. So we'll start with some basic definitions and build our way up. So let's begin by talking about a random experiment definition. A random experiment is a process whose outcome cannot be predicted with certainty. Right? It's random if you can't predict the outcome with certainty. So for example, flipping a coin is a random experiment. Sure, you know what the possibilities are, could be heads or tails, but you don't know for sure which one is going to land on in general, right? Or the roll of a die, right? You don't know for sure which side is going to show up. So this is called a random experiment. Probability seeks to measure this. Probability seeks to measure the likelihood, quote unquote, or chances, quote unquote. And by that, I mean, i.e. relative frequency. Just like some sort of proportional measure of how much more often one thing will occur as opposed to something else. Of certain, maybe I shouldn't use the word certain. I mean, it's fine by language, but of various outcomes. Various possible outcomes of a random experiment. Right? So like the coin flip or the die flip, right? So I told you guys that probability really was developed as the mathematics of gambling. So gambling, there's a game of chance, right? And you want to know, what is the likelihood that I can win this game that I'm playing? What is the likelihood that I can, somewhat knowing what the chances of something happening, even though the future is uncertain, that I can position myself well? How do I know when to keep going, when to quit, when there are good odds of me succeeding, when there are bad odds of me succeeding, things of that sort. And of course, by that kind of description, you can kind of sort of see now why probability is useful in general. statistics and probability are very useful in everyday life. You use it everywhere, everywhere, more than you realize. And in some sense, and this is definitely an oversimplification, but in some sense, you can think of things like AI and machine learning and that sort of thing as just a little bit of probability, statistics, linear algebra, calculus, and a dash of computer science in there too. But yeah, so even when you're talking to Siri and she's answering you, Siri, tell me a joke. She has to calculate what is the probability that if she tells this random joke that you're going to laugh, and Apple would be very interested in that probability being high, because if you like what Siri says, you'll continue to use Siri, and then they can get you into their ecosystem and trick you into getting an iPad, right? So it's very important for businesses and whoever to kind of know what the chances of something occurring, and kind of take advantage of that, as well as all these things where they set up programs to kind of do Turing tests where you have a conversation with a computer. The computer is really doing a bunch of probability. What is the likelihood that if this string of words is used, that it would make sense in response to this question that this human just asked me? And it calculates probabilities in very rapid, sophisticated ways, but that's what it does, right? So the man went to what is the likelihood that the next word would be store, and that would make sense, or balloon, and that would make sense. Well, it wouldn't make sense. It would make less sense to use the word balloon than store, right? So it'll compute all these things. So it's used everywhere. So you have a cell phone, probability is being used against you. You have insurance, probability is being used against you. Like you have probability is everywhere in your life, everywhere. Okay, so because life is a random experiment. You don't know what the future holds. You don't really know what's going to happen tomorrow. Sure, you know a bunch of possibilities. Oh, I'm supposed to go out with my friends, but you don't really know what's going to happen, right? Surprises happen all the time, and probability helps us in this situation. How do we actually go about getting these probabilities, though? So let's start to build that up. Definition. Someone's coming in here. Let them in. The sample space of a random experiment is the set. I want you to realize that it is a set. So obviously, set theory is going to be very important when we're talking about probability. Is the set of all possible outcomes of a random experiment. So you flip a fair coin, the set of all possible outcomes, it was going to be the set containing H and T. You can get heads or tails. That's all the possibilities. If you roll a fair die, set of possibilities 1, 2, 3, 4, 5, or 6, right? You know what the possibilities are, you just don't know which one is going to show up. So that's what a sample space is. It's kind of a set that contains all possible outcomes. Definition. The elements in a sample space are called sample points. Yeah. So each possible individual outcome, we call it a sample point that lives in a sample space, the set of all possible outcomes. Let's talk about what an event is. An event, you can also call this an occurrence, but an event is a subset of the sample space. right? So that's how we're going to think about the word event from now on. There's a set of all possible things that can happen. Any subset of that set is called an event, right? So I can talk about the set of all possible things that can happen when I flip a coin. The set is H and T. Me getting heads, which is just the set containing H, is a subset of H and T. That is called an event. Me getting the heads would be an event in this experiment. Okay, so this is going to be important later. Definition, sample points in a sample space are called equally likely if they all have the same chance relative frequency of occurring. Okay. For example, you flip a coin. You have two possibilities that can happen: heads or tails. Then there is you might want to consider, well, am I more likely to get heads or tails? Like, which one will happen more often? And it turns out, in the case of a coin, they will both happen with the same relative frequency. You'll get heads almost as many times as you'll get tails on the aggregate. So it's actually, fun fact, impossible to create an unfair coin, right? Any coin that you create will have, you will have an equal likelihood of getting heads or tails. This is not true with something like die. You need at least a third dimension to make that not happen. The only way to actually create an unfair coin would be to bend it slightly. You'd actually not really have the coin. But that's just something that's interesting. But yeah, so equally likely just means you expect them to happen roughly the same number of times, any event, right? So that's going to be important. There are certain things that would apply to equally likely events that wouldn't really apply to other events. Okay, so now one thing I do want to mention is that in this course, we will always consider the sample space to be a finite set. We already spoke about what finite sets are. So this is finite probability, right? So we are always going to think of the sample space as a finite set. This does not have to be true in general. Your sample space can have infinite sets. Subsets of your sample space can also be infinite sets. Sample spaces can get quite weird, and the probability that goes along with those sample spaces can also get weird, and you'll need calculus and a whole bunch of other stuff to do probability in that case. We're not going to be doing calculus. We're going to just be doing probability where we can count everything that's going to happen and count the things that we're interested in and move forward with that. So yeah. So now let S be a sample space with equally likely events. Sample points. And so another common notation for this it's the uppercase Greek letter omega. Yeah, but I'll mostly use S because omega is kind of weird to write quickly. Omega. I'll mostly use S just because of the ease of writing. And I think your textbook uses S. I don't remember. It's been a while since I read it. I kind of do my own thing. I just kind of look at the textbook for what topics I should teach you guys, but I kind of teach it how I want. So I'm not sure what notation your book uses, but it's probably one of these two. I will be using S though. So every time I write uppercase S in a probability context, I will be thinking about the sample space. Let A subset of S be an event. Okay, then I'm going to define for you what a probability is. Definition. The probability of A denoted P of A or boldface P of A, which I won't be using very often because it's harder to write. I'll use the first one, is given by P of A equals the size of A divided by the size of S. I should probably say that sample spaces are always considered to be non-empty. Because if you're in a situation where nothing can happen, like why are you even measuring probabilities? S is always considered to be non-empty. Okay. So you'll never, for example, divide by 0. Okay. An event can be the empty set for sure, but the sample space will never be empty. There has to be something that could happen, right? And so this is the number that we call the chance of A. Or the likelihood of A. Okay, and obviously counting is important for this. Okay, because we're going to be measuring sizes of sets. We want to count things in a set, right? So let me do a very basic example about how we are going to think about the process of finding a probability. Now, of course, this example is very simple, and a lot of you will know what the answer is without going through anything, but I want you to see how you would go through something in theory, because it's going to give you a very good principle to follow. So, example. You flip a fair coin, which is very superfluous. Every coin would be fair, technically speaking. What is the probability? But when we say fair coin, we usually just mean a coin where one side is heads and tails. What is the probability that you get heads? That's the side of the coin with the dude's face on it, right? Okay. Now, everyone knows that the answer is a half. We all know this somewhat by intuition. That is what I want us to get away from. Your intuition will lead you astray when it comes to probability. So I want you to learn how you want to think through a probability problem. So what you would do here is you would set up the sample space. Here, S is H and T, right? Set of all possibilities. You can get heads or tails. I want you to also appreciate that the size of S would be 2. And let A be the event, we get H. So that would mean A is going to be the set containing H. That would mean the size of this set is 1. And so this would mean the probability of A is going to be the size of A over the size of S, which is going to be 1 over 2, right? Which is the intuitive answer that we'd all have guessed it was. But where did that answer come from? Well, it came from considering this. And then we just all kind of knew that that's what it is, right? There are two possible things, and only one of those possibilities in H. The relative frequency is then is going to be 1 out of 2, because they are equally likely. If it wasn't equally likely, it would not be a half. And this is why your intuition can lead you astray. Events that are not equally likely can throw a wrench in things, and so you have to be careful. But yeah, we have that example. Okay, so that is kind of how you would go through the process. Now, of course, something like flipping a coin, I expect you guys to all know that the answer is a half to get heads, but we're thinking through it very slowly. We want to build up a good set of rules. So here is the basic process. Is someone saying something?
Sorry. Could you scroll for 2 seconds? I have a quick question.
Oh, yes.
Just how exactly did you find like S equals 2 and A equals 1? Just like...
Oh, I didn't. This is the size of S, right? I have these bars here.
Okay.
Right, so I'm just measuring how many things are in S. This is the cardinality of S.
So heads and tails, so 2.
So heads and tails, there are 2 things in that set. Right, this is the size of S. And this is the size of A. Okay, so A is a set, and S is a set. And once I conceptualize those sets, now I just want to know how big are they? How many things is in each set, right? So that was 1, 2, and 1 respectively. And then I just divide those 2 numbers. So let's talk about the basic process for finding probabilities. TFA. Okay, so this is kind of the real basic process that's always kind of happening in the background. There are times when I'm going to teach you some shortcuts and formulas and tricks and strategies where you don't really have to approach it this way, but that's because those formulas and tricks and strategies would already have considered all these steps, and then we can do it. But when it comes down to you're in an unfamiliar situation, you don't know what the probabilities are, you kind of want to follow this route. So as I mentioned here, we'll cover some tips, rules, formulas, strategies for covertly doing this. Later, right? But this is the very basic process, okay? So one thing you're going to do is, one, you're going to create a sample space. Of equally likely events. Okay, and by the way, this tends to be the hardest step. Creativity and experience may be needed. The other steps are in general easier, but they can also be difficult, right? Now, when it comes to this class, like I said, we're not going to be tackling the craziest problems. So I will give you some strategies for creating a sample space, what to consider when creating one for the situation that we're doing. But creating one is often going to be the thing you need to do. How do you conceptualize all possibilities? 2, you are going to find the event A in S that you care about. It will be a subset. Okay. 3, you're going to find the size of these guys. Find the size of S and the size of A. And then finally 4, P of A will be the size of A divided by the size of S. And that is the simple 4-step process for finding a probability. It's simple. It's not always straightforward, right? So this is pretty much what you want to accomplish when computing any probability. And yeah, I can give you formulas and rules and strategies and tips, but ultimately those guys will be geared towards getting you through these 4 steps, right? That's what's going to happen. You'll notice that that's how I thought through this. Heads or tails, what is the sample space? What is the event I care about? What is the size of the sample space and the size of the event I care about? Once I have those, I can now do the division and find the probability. Okay. So that's a very basic steps. Measure the size here. Okay. Now, probability, like all of math, is based on axioms. Okay. Now, axioms, these are mathematical rules that are self-evident, right? So they are rules that we consider to be true, even though we have no justification for it. We do not seek justification for it. We don't try to prove it. It's just the rules of the game, right? So a lot of people think that, you know, math is this thing that's, you know, it's ingrained in the universe and, you know, it's given to us by the gods and we're slowly discovering it. And, you know, it's very, you know, sometimes it's just not meant for us. And, you know, I'm not a math person, blah, blah, blah. Really, math is like a game, pretty much like chess. It's a very complicated chess game, right? We set up the rules arbitrarily. The knight moves like this, the queen moves like that, the king moves like that. And then a game can be very complicated and it can be very challenging to get through a game, especially if you're playing with a skilled opponent, right? So math is very much that way. It's built upon these rules that we don't have proof for. We just say, let's pretend this is true. Everyone agrees? Oh yeah, we all agree. All right, now let's develop a set of rules that we will consider to be logical, by which we can use all these things that we assume to figure out other things. And that way, we kind of rescue ourselves from our intuitions. And so the math can tell us a lot of useful things that we as people probably wouldn't have come upon. And that's why it looks magical and mysterious and like, wow, like it's so useful. Like math is I don't know if this is meant for me, but really, no. It's we came up with rules that make sense in our universe. And then we came up with logical ways to use those rules to derive other facts. And so when those facts surprise us, because they aren't beholden to our intuition and they are surprisingly useful, we're like, oh my God, math. But really, yeah, it's a glorified chess game, essentially. So just like with chess, sure, you might not have it in you to become a grand master like, you know, Magnus Carlsen or anything, but you can learn to play chess, right? The average person can learn to play chess. In the same way, the average person can learn math, right? You're probably never going to be, oh my God, like Einstein or Newton or Gauss, but you can be good enough to accomplish a lot of things, right? Too much ranting, let's move on. So let's actually talk about those guys, the axioms of probability. Okay, so these are the things that we will hold to be true, and I'm not even going to justify them to you because there is no justification. It's just how we're setting up the game. One, for any event A, P of A is a real number such that the probability of A is between 0 and 1. This is a very important rule. Probability will never be anything outside of 0 and 1. Not for us anyway. Sure, there are times when you want to set up your probability so that it can account for negative numbers, complex numbers, and things of that sort. But these are some very strange applications. Quantum physics, string theory, and things of that sort, where you're just kind of having some crazy situations. You might want to expand your definition of probability. But a lot of probability, most of probability, and definitely, certainly probability for us, it will be a number between 0 and 1. And I highlight this because I do want to just be upfront with you guys and be like, if you ignore this rule, you will likely be punished very heavily for it. So if you do a problem and you tell me, oh, the probability is 1.7, I'm going to probably take off most, if not all, the points for a mistake like that. If you tell me, oh, I got the probability of 1.7, but I know it's wrong, I just can't find my mistake, I'll be a lot more lenient. I'll kind of find where your mistake is and deduct points for that. But you should know the probability should always be between 0 and 1. If you get an answer outside of that, you should know you're wrong. You're definitely wrong, and you should acknowledge it. And then, you know, that will cause some leniency. By the way, this means the probability of the entire sample space will, by definition, be the size of the sample space over itself, which is 1. And the probability of the empty set, which is going to be the size of the empty set over the size of the sample space. This is 0 over the size of the sample space. This is 0. So the probability that nothing is going to happen is 0, right? 0 is kind of like the 0% chance. I don't want to say it's impossible. Probability of 0 does not mean impossible. We'll probably talk about this a little bit more. That's a very common misconception. 0 is usually thought of there's a 0% chance. 1 is thought of there's a 100% chance. But it doesn't mean it's impossible or it has to happen in general. We'll talk about that later. But we can know from this axiom that the probability of the entire sample space is going to be 1. In fact, it's nice that that worked out in the definition, but that's actually an axiom. The probability of the entire sample space is 1, right? The probability that some event in the sample space will occur is 1, right? That's basically what that's saying. Something has to happen, right? If there's nothing that can happen, you don't even have a sample space. Why are we even talking about this? Like, nothing's going to happen. What are we trying to measure exactly? What are we trying to predict? So the third is one that gets people in trouble because they don't really pay attention to it. But I'm going to highlight where the important part is. If A1, A2, ... I have n sets, AN, are disjoint subsets of S, right? So they are disjoint subsets. That is the key word, disjoint. Okay? What I'm about to write down is not true in general. It is true if they are disjoint. And this is the axiom that we take for disjoint sets. Then the probability of A1 union A2 union ... union AN is the sum of the individual probabilities. Okay, and this is the third axiom. If I have disjoint sets, and remember what disjoint means, I reminded you guys of that yesterday. This is what disjoint means. They have an empty intersection. There's no overlap. You can't have something happening in both at the same time. Okay, so if your sets do not intersect each other and you want the probability that this event or that event or that event or that event is going to happen and they don't have overlaps, you're allowed to add them, right? And we sort of did this with a counting rule as well. The counting rule is kind of why we wanted to invent this axiom. That's it. 3 axioms. So the thing about inventing rules about that you don't even want to justify or prove is that they need to be minimal, because the more you start sitting there making up rules and rules and rules, the more your human intuition is going to sneak in there. So you want to keep things very basic, and you want to get away with as little rules as possible and then derive everything else logically. Let me measure this again. That's it. Using the logic of mathematics, using the rules of set theory, we will go from these 3 rules to every rule of probability. Every rule of probability can be traced back to these 3 rules. These are the beginning, the periodic table of probability, right? Everything is built from these 3 rules, okay? Now I want you to realize we have what is called the law of disjunction. This is what is going to generalize the third axiom. The third axiom works in a very specific case when the sets are disjoint, but they don't have to be disjoint. So if A, B are events in a sample space, then the probability of A or B is the probability of A plus the probability of B minus the probability of the intersection. So that is true in general. This is always true. Right? It's always true, right? In the event that your intersection of A and B is empty, like they're disjoint, what's going to happen is that this part here will give you 0 because of what I said right here. And so you end up with just the sum of the probabilities like in axiom 3. So this becomes axiom 3 once you take away, once you force the sets to be disjoint, because then that part won't apply. And yeah, but that is how it would work in general. And again, everything falls back to the axioms. So you might wonder why does that have to be the case? Well, what is the probability of A union B? By definition, this is going to be the size of A union B divided by the size of S. However, we know what the size of A union B is. We covered this a while ago. The rule that tells us what the size of that is called the inclusion-exclusion principle. So this is the size of A plus the size of B minus the size of A intersect B. We spoke about this a while ago. This is by the inclusion-exclusion principle. I don't remember what lecture I spoke about that in, but I did talk about it. Okay. Now, That is true by the inclusion-exclusion principle, so that is a logical step. Something else that is a logical step is that I know how fractions work. I can split up the fractions across the denominator like so. And now what's going to happen? Well, by definition, what is the size of A over the size of the sample space? Well, that is the probability of A. What is the size of B over the size of the sample space? Well, by definition, that's the probability of B. What is the size of the intersection over the size of the sample space? Well, by definition, that's the probability of the intersection, right? The probability of anything is the size of that thing over the size of the sample space, right? And so you get that rule. That is a general rule. It has to be true. We can get to it by the definition of probability, how fractions have to work, and what our definition of probability is again. So that's definitely going to be true all the time. Also recall something from set theory. The universal set is a set union its complement. In probability, we always consider our universal set to be the sample space, right? It's the set of all possibilities, right? It's the set of everything. So this would mean that the sample space can always be thought of as any event union the complement of that event, right? And this would mean that the probability of S is the same as taking the probability of this, because that is equal to S, right? But A and A complement are disjoint, right? Remember, A complement is just a set of all things not in A. And so this means that the probability of S is equal to the probability of A plus the probability of A complement. And so this means so this is by axiom 3. And this means that 1 by axiom 2 is equal to the probability of A plus the probability of A complement. We can actually rewrite this as the probability of A is 1 minus the probability of A complement. This is a very important rule. It's called the complement probability formula. And what it says basically, i.e., the probability of what you want, right? The event you're interested in is 1 minus the probability of what you don't want. Right? And this is true in general. And the complement formula is useful when it is easier to count points in the complement than in the original set A. I'm going to just run through a quick example to kind of let you guys see what this is, and then I'll let you go. I'll in fact leave some examples for you to try next class. try for next class, which I'll leave posted in the notes, but try these for next time. Example 8 is going to be very interesting. But for now, just going to run through a quick example to show you how the complement probability can be useful. Example. See what the notes here. Okay. You flip a coin three times. What is the probability you get at least one heads? Right. I also want you to recall at least means greater than or equal to. And at most means less than or equal to. Okay, so I would say let A equals the event you get heads. Okay, so what does that mean? The at least one heads. So what does that mean? The probability of A is the probability that you get one heads or two heads or three heads, which means that's the probability of one heads plus probability of two heads plus probability of three heads by axiom 3. Because these are non-overlapping, right? If you flip it three times and you say I got one heads, you couldn't have gotten two heads at the same time because you wouldn't have said you got one heads, you would have said you got two. So these guys do not overlap, right? So now, in general, there are many situations here. Right, so think about getting one heads. Well, when would you get it? First or the second or the third? There are three possibilities there. Okay, at two heads, how can you get it? Well, you can get the first and the second, or the first and the third, or the second and the third. Like you'd have a bunch of things to count here. However, but what is a complement? This is the event you don't get at least one head. But guess what? That is actually super easy. That means you got all tails. And really, there's only one way for that to happen. So that's actually an easier thing to count, right? So you can go and you can kind of set up your sample space. So, okay, so S is equal to the set of X, Y, Z such that X can be H or T, Y can be H or T, Z can be H or T. So that's my sample space. It'll have a bunch of things in it, like heads, 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 tails, a bunch of things, all the way up to tails, tails, tails. Okay. Then you can let A be the event that you get at least one H, right? So that would be, you know, heads, 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 tails. It's going to go up to, who knows? But you must have an H in there. But that would mean that your A complement is the guy that only has TTT. So now You can say the size of S. Well, what is that? Well, this is the number of 3 tuples with 2 options for each entry. Right? That's what we're actually counting, right? So this is going to be 2 cubed by the multiplication rule. So there are 8 total possibilities. Now you go and measure A, and you realize, annoying to do. So instead, measure A complement. Which is easy. There's only one. So now you can find the probability of A is 1 minus the probability of A complement. This is going to be the size of A complement over the size of the sample space. It's 1 minus 1 over 8. And so you get 7 over 8. There's a 7 over 8 probability, a 7 over 8 chance that you would get at least one head. Right? So that's an example of using the complement probability. And I really want you guys to try this for next time. Very important. Probability is going to be a very strange endeavor for a lot of you. So you really need some practice, a lot of practice. So be sure that you put the practice in, because it's something you're going to have to just get used to. Yeah, like knowing when you should look for the complement as opposed to not. Maybe it was easier to do it directly. You don't know. Well, you will know eventually, but we'll stop there. I already kept you guys way over time. So I assume your coaches will be reaching out to you soon. They probably already have if they have your schedule already. And yeah, we will stop there. Have a good weekend, work on those problems, and I will see you guys in the next one.